So what I'm going to cover today is how big data can be used for solving spatio-temporal problems. The topics that we'll be broadly touching are the following. One is biophysics, biochemistry, and drug design. Then we'll also see molecular dynamics simulations, a little bit of complexity analysis that is related to computer science and big data tools. As you can see, it requires multiple backgrounds or a lot of exposure to various completely different kind of background that is required. So some of you might be more comfortable with one or more of these four. So it might look as if I'm taking it to a little lower than expected level, but please bear with me because we have different, we have large number of students with different backgrounds. So I'll try to, my attempt at this talk is to convey what are the basic concepts that are involved. And if I'm able to convey to you the actual idea, I'm sure if you're interested, you'll pick up whatever tool set and skill set that is required to apply in whatever domain that you'd like to work. So let's say that we have some biomolecule, let's say DNA, and we want to find waters that are interacting with this one. Now, the question is, why is it so important, right? Why is it difficult and why is it important? So first, let us look at it and let's see why this is an interesting problem and why it is also a tough problem. So there are several reasons why one would like to study the waters that actually interact with biomolecules. Firstly, the stability. You see that there are three different forms of DNA, which is the blueprint for all living beings. And you see, it is also very well known that you can, hydration, basically water really can play a role in, changing the conformation. We say conformation whenever we refer to shape of molecules. So water really plays a role, and it has been shown that hydration really affects shape of molecules, not just DNA, but any biomolecule. And this talk is not just related to either nucleic acids or proteins. It is a generic one, and the concepts can be used elsewhere also. But this is just to show where actually finding the influence of water would be of very would be of relevance and would be of interest. So the second reason why we would like to know how water influences is the conformation. And the molecule that you see here on the left-hand side bottom, it is called ribonuclease A, and that is associated with multiple Nobel Prizes. So one of the first prize was for solving a problem. Rather, there was a puzzle which is called as Levithal's paradox. So if you make a crude model for protein is nothing but a chain of polymers, and there are 20 different types of units that make a chain. So it is known that many of the biomolecules actually take a particular shape, which is of biological significance. For example, if you make a polymer that defines this particular molecule called ribonuclease A, it will always come to this shape, and it is necessary that it should come to this shape so that it can function whatever that is expected of it. So shape is very important. From now onwards, I'll use conformation, which is the more technical word. So, and also to initiate folding process itself, it is known that water actually contributes to that. And functioning also gets affected by water. What you see here is a rhodopsin molecule, and rhodopsin is found. So what happens is there are molecules that stay in two types of states. One is on state, and one is, you can say, off state, just like an electrical switch. So there are times when you want to switch on the activity. So you do something and the molecule starts functioning, or you do something and then it stops functioning. Okay, for example, if a signal has to be received by rhodopsin, which is a GPCR, so GPCR is one of the types of important proteins. So what happens is it functions only under certain conditions, and you can switch on or switch off these activities. And this kind of activity is found across the entire biological process. I mean, you have to decide when to make some particular molecule and when to stop making a molecule, when to send a signal, when to stop sending a signal, and so on. So there are switches, and water, in fact, ingress of around 80 water molecule really changes the state from active to inactive and vice versa. So again, you have catalytic activity. You know what catalysis is. So basically, there is a chemical reaction that is supposed to happen, like what is shown here. There is a large molecule at the top which gets split into two through a water molecule, and that's the reason we call it as hydrolysis. So to do this, I mean, if there is no external help, then it will take a very long time. But if you want to do it at biologically relevant time scales, you can speed up the reaction by a million-fold easily. And for that, you need some catalyst. So the catalysts, the proteins that function as catalysts are called as hydrolysis. And the study that we are going to see now is actually on one of the hydrolysis, which is of interest and is related to COVID. So water is important because we want to understand how it actually helps or hinders certain kind of activity. Also, there are three different types of tasks that can be done, and all of them can be explained with the same slide here. So you have what is called as a target and a ligand. Ligand is generally a smaller molecule. Target or receptor is a larger molecule. So this ligand, the small molecule, normally gets bound to the target, and then it accomplishes some task. I mean, it can be used either to do something or stop something from happening. For example, if it is necessary for SARS virus to replicate or for its propagation, then we can block its activity by, sending a drug molecule or some other molecule that will go and bind, and it will make sure that it does not function. So, or sometimes, you may want to enhance the activity, and even for that, you require ligands. And it has been known and it has been shown that for ligand binding and rejection, to optimize ligands for binding, and also to perform free energy calculations, which are at the core of drug design, right? So it has been known that you need to understand there are some special water molecules which are sitting nearby, which are interacting, and you want to know where they are and how they actually are interacting. So water plays it's there and it plays lot of roles. So for this interesting question that we would like to find where the waters are going to come and bind, there is a standard and obvious way of doing it. If you come from the background, you will say that we'll use X-ray crystallography. It is like, you take pictures of that particular molecule whose association with waters you want to study. Of course, you cannot do that with a single molecule. So what you need a crystal, and you can use advanced techniques that are available nowadays. And then you can find out what the molecule looks like and where the water molecules come and interact. Okay, so this is a very, very powerful technique. It gives a lot of information, something that is always gratifying to find, because you can model many of these, but many times certain small deviations is what is going to determine whether your understanding is either correct or wrong. So you need to have as much accurate information as possible. Now, there is a problem with, there is an issue with this kind of approach. As you can see with the third slide, all those balls that you see in yellow, they are all water molecules. And this is a crystal structure, and the PDP code is 1 DNA. So you see they sit nearby, and some of them are not nearby because, because of crystal packing, certain positions in 3D get stabilized. So you will find water molecules, but those water molecules have no physiological significance. They are there because you are taking picture of a crystal structure, and you're trying to understand what a single molecule looks like. A single molecule will never have those additional water molecules stabilized. Firstly, because it will be in water most of the time, cytoplasm or wherever nucleosome it is. So there is a lot of water around, but then there are some that are actually interacting with it, and those are the ones that we would like to study. So how do we differentiate which are the ones that are fundamental to its functioning and which are the ones that are, just there, and there are others that are there, but they are not supposed to be there. I mean, you have three different classes. One that is required for the functioning or its existence because it also provides stability. Second is because of its structure, certain places become favorable for water to interact. It's not that these waters are actually contributing to any of its functioning, but then they are there. So no profit, no loss kind of situation. But the third one are all spurious ones. So how do we know? How do we understand? Rather, how do we find out and ascertain which are the ones that are functionally important, so that for the issue at hand, for example, it could be drug design. We want to understand where the water molecule sits, and maybe we can use something to find or fine-tune a drug, or if we can understand how much free energy is actually there, absolute free energy, and how much can it be really improved. So for this, there have been cases where only inclusion of water molecule have given correct answers. So yes, X-ray does give a lot of information for us. You can see on the left-hand side, there is a cartoon representation. There is a ball that is hanging with a thread. It is actually a switch. So it is voltage gated ion channel. It's a schematic diagram. It's a cartoon representation. So what happens is within the way in which our body functions, there has to be movement of ions across. A lot of other compounds, but also ions. What I'm showing you is ions. So you can see there is no room for any of the ions shown again in yellow balls that you see. Probably it can be, you can consider them to be sodium. So they have to move from the top side to the bottom side, but then it's blocked. It's blocked by that yellow, that blue ball. So it is called as off state, OFF state. So we want to understand from the crystal structure that you get, because crystal structure only gives you one picture. It gives you a lot of data. Please do not, underestimate the importance of crystals having crystal structure. For example, if you look at this picture, you can see that you can get a lot of details. You can see there is a kid, there is his mother. You can see there is some furniture around, plants, balls, and also you can you get decent amount of very important data. But then what we are trying to understand is not the static information. We get static information because unless all these proteins that we are actually trying to crystallize, or we have crystallized, unless all of them look identical, we won't get the crystal structure decoded. So, I mean, that's how, that's the first requirement. All the molecules should sit exactly the same, or maybe in one or two slightly different orientations. But then repetition is something that is fundamentally, it's a fundamental requirement. So what we have is static data. And because all of them are sitting nicely, it is, as you would expect, It is a minimum energy state. But this is not how anything functions. I mean, in reality, if this is an ion channel, it's not a channel because either it will always be open or it will be closed. We want to understand the dynamics of it, how it gets closed, how it gets opened, what are the residues or what are the atoms that are atoms or molecules that are involved, so that you get some understanding. So we simulate or we need to have some dynamic information, right? So how do we do that? So with single picture, now we have to generate dynamics uh, in some way, which you should be able to verify and validate later. And that it has been done a long time back. We use what is called as molecular dynamic simulations. So what's the idea of molecular dynamic simulations? We use to begin with Newton's laws of physics. You know, whatever we studied in our school is what we turn to. And first we'll put that information that we have gathered from either X-ray, or you can even do modeling, and excuse me, you can place atoms at some position that you think makes sense. So, which is what is called as setting up the system. Then we have to model the interatomic forces. So we have to decide what are the forces that exist and what are the parameters for those forces. For example, bond length. If you have a covalent bond, you can have two different models. One is of a spring, a harmonic motion that you can replicate, or then you look at the data and you see, you know, it doesn't really make much difference. The bond length does not really change much. So I'll assume that it is always going to be constant. So we are actually putting an additional constraint that the bond length always remains the same. And no matter what we do with the simulation, we ensure that bond lengths remain constant. So that is something that we model. We choose a model. We have to make sure that it makes sense. We have to validate our approach. But once it is done, and this is more or less has been validated long time back, so there is nothing new in it. So we use any of the standard force fields. So basically a force field tells us what are the different forces that act. There are forces that act because of electric charges. There are some atoms that are positively charged, some are negatively charged, some are uncharged, some have dipolar movements, some have van der Waal interaction. I mean, there are van der Waal, not some, all of them have van der Waal interactions, bond length, bond angle, what is called as torsion angle also is there. So there are many degrees of freedom, and we have to see whatever is good enough for the model. Now, you have to remember that we can never replicate nature. We only make model, and we can always see how closely it matches. Okay. Because there are always going to be very, very small, insignificant deviations. So you have to decide if the deviations you are going to get are acceptable or not. Okay. And also, even though you may come up with a very good force field, much better than this, you can take quadruple movement and so on. But the problem is, computationally, it might turn out to be prohibitive. So you may not be able to set up the simulation, or it will take forever to, you know, give any useful information at all. So what you do is you see what are the forces you want to include, what are the constraints you want to additionally impose. And for example, if you have van der Waals, you can use two different types of formulas for them. It's a textbook stuff if you know, but otherwise we'll choose the one that is more amiable to competition, but also at the same time gives very good results in agreement with the experiments. So the first step was to set up the system, put atoms where they should be to begin with. Then we'll say we'll set up the forces that interact, and then we set the atoms to motion. We say move. So how do they move? We move because we tell computer what should be the new coordinate. How do we do that? So we again use, I mean, this is a consequence of Newton's laws. We'll not get into why this is correct, but what this shows is if you know or if you assume initial positions and initial velocities, then using the first equation at the top, you can find the new position after a time t plus delta t. Delta is a very small fraction. Normally it will be like 1 femtosecond, 2 femtoseconds, sometimes even 4 femtoseconds. So you know at time 0, so you want to find out the position, new position of every atom. This we do for every atom after delta t. And using that, you can find the acceleration at the time step t plus delta t. Using position and acceleration, we can find the new velocity. So what we need to begin the movement or set the system into motion is the initial state. So the initial state is nothing but we have to give the coordinates and the initial coordinates and initial velocities. If we give initial coordinates and initial velocities, you can then compute the coordinates after delta t and velocity after delta t. Again, using this, you can put it in a loop. You can find coordinate and velocity after time t plus 2 delta t and so on. So this is how you put atoms into motion. And what we do is at regular intervals, we take, we note down the positions. But before we go there, just there is one small detail I would like to cover. So as you can imagine, the first step, the initial step is always going to have some issues because, you know, it's a modeled one. So what we do is we neglect certain initial part of the simulation till it reaches an equilibrium. So that again depends on the type of the system and size of the system. The larger systems take longer time, unsurprisingly. Okay. So for the systems that I'm discussing, it takes a few hundred nanoseconds, and that's a lot because we are talking about, you know, femtosecond is, I mean, 1000 femtoseconds make microsecond, sorry, picosecond, and 1000 picosecond gives microsecond. Now there are simulations that are done for milliseconds also, but you need either very small systems or very big computers that, you know, very few have. So what do? We save the frames just like, you know, we used to do for, I mean, people have been doing it for movies. What we see here is movie, which tells the dynamics, which shows the dynamics of the system. The way we have saved is we have saved frames. So every frame here corresponds to XYZ coordinates of each atom at a different time. So the first one could be at time, let's say 100 nanoseconds. The second one is 100 nanosecond plus delta t. Third one is 100 nanosecond plus 2 delta t, and so on. And then you can play the video. You can see what happened during the simulation, and you can start writing programs to understand and to derive the dynamical parameters. Okay, so that's what we call as deriving properties from the system. So how do we actually make sense of the data that we have generated? So now we have frames. So that means we have large number of sets of coordinates at different times. Okay. So what we can do is we can put all of them together, but you know, the molecules move. So we have to make sure that we have to do a best fit. So if you see the figure here, I do not know if the is the cursor visible at your end? Never mind.
No, sir. Okay.
Hello?
Yes, sir.
Cursor is visible?
Yes, sir. Yes, sir. Cursor, yes, sir, it is visible. It is
Right,
visible.
thank you. So, because unlike in a X-ray based output, we have now the system in motion. So you will never find the same shape ever. I mean, you don't expect that to happen actually. And you can try to fit all of them in a very nice fashion as best as possible so that there is least deviation possible between the corresponding atoms. So if you look at it, there are certain regions where you see that there is a very nice fit, and there are certain regions where there is a lot of movement, and then there are certain regions that you probably may not even see if you're doing something like NMR studies. These are all wildly different states, and there is always going to be uncertainty. So there is certainty for certain regions, there is lesser certainty for a few, and there is a lot of uncertainty for others. And what we're trying to do here is we are trying to find waters that is interacting with the DNA. Now, what happens is if DNA keeps on changing shape, water might be moving with it. But if you superimpose, this is called superimposing or overlaying, it won't give you a really good idea as to it does not really tell you immediately that there is an association, because everything gets smeared. Like at equivalent positions, there could be water here, but because if you start doing statistical analysis, you are going to run into trouble for certain cases where it is going to be uh, challenging for the dynamic ones. But then there are two different types of approaches that you can take. The first one is you superimpose all of them. You take density of waters in space, convert them to an X-ray like configuration. This basically, whatever mesh that you see shows the higher probability regions, probable regions where you will find water. And we are lucky here because this is DNA. If it were a protein, something like this, there will be too much of uncertainty. Okay. And then we try to assign the coordinates for water molecules just as we would do for the regular atoms of DNA. This is one way in which you can work. The other way is you divide space into cubes or grids, 3D grids, and then you say if there are at least 50 or 60% of waters that are there. For example, the bin size is something that only one water can sit at a time, and you see that out of 100 frames, 60 frames have water. Then you can say, okay, there is a water there. You don't expect it to be there in all, but then that would be another way of doing it. But as we know, there is a problem. What is the problem? The problem or the challenge comes for the regions that are not really so nicely superimposed. For example, if you see most of the, whatever that you see here, hardly anything changes. There is only one item that is changing. That is one swing, one of the two swings. The rest of the equipment is stationary. But what we are looking at is the girl always associated with the balloon? Now, if you take pictures and then if you do superimposition, you see that there is motion blur for the girl, for the little girl, and there will be motion blur for the balloon. And whatever cutoff you might put, that may not make any sense, because what happens is you have to remember, if you do not, there is not just one balloon that is floating around. What we are looking for is that particular balloon that is associated, something that is actually she is holding to. If you put some, in physiological or cellular conditions, or even in simulation conditions, this protein is sitting in thousands and zillions of water, whether it is experimental or theoretical. So we really would not know whether there is an interaction or not. The only way in which we can do is we take pictures, and then in every picture we make a decision whether or not she is holding, and then we put all that information together to decide during this simulation whether there has been an association or not. So that is the idea that I want you to first get as to what is the challenge that we are talking about. So if you are talking about a case where overlaying structures has little change or little variation, and waters also come out very nicely superimposed on them, then it is fine. But then you don't expect that to be the case, especially if you have more interesting proteins rather than DNA or something like that. Proteins are huge. They're really huge. So in such conditions, it becomes very difficult and very challenging. But then the importance does not come down. Okay, so how do we model this problem? Because if you can come up with a model, if you can model, you don't have to worry at the moment if you can do, programming very well, or if you can, if you're good in big data, or if you have ever heard of big data. The point is how to define a problem. If you are able to define a problem, you will find a solution. Maybe you may have to sit on it and gain more expertise or talk to people who are better in that particular area, discuss the issues, but then you have to be able to communicate what exactly you want uh, to be the output. Okay, unless you can define what the problem that you are looking at. I mean, what we have in this cartoon is a goal. We want to find that, whether or not that girl is associated with a balloon or not. So, but how do we actually put it in a fashion that can be programmed or that can be evaluated, and then we can be sure that the answer is going to be correct? So for that, you have to model properly or whatever appropriately. And then we look at what is the tool or what are the tool sets that you have to apply to be able to solve that particular problem. So here I'm showing you a model that I actually used during my PhD. Actually, it was after my PhD. So this was not published, but the later version was. So I'm just showing you what exactly we mean by identifying frame-wise data. From frame-wise data, whether or not some water molecule is associated with a set of atoms. Okay, so the definition is now in front of you. Here, what we do is we use a term or concept called network. So what is a network? Here we have a network, and a network is defined as following. There is one common water molecule that is having interaction with two or more polar atoms. I mean, those polar atoms should not be waters. That is something that should be clear to you. Because, so this water molecule will form a network only if there are two or three. Here, there are two different atoms that are interacting with this common water. Here, there are three. So this is network one. The identity is not given. Let's say this is atom A, this is B, this is atom C. Here we have atom D and atom E. So D and E form one network, A, B, C form another network. And I mean, earlier I was, I tried to find, and I did find actually the interaction between networks itself, but they are not very strong. So the newer version with big data does not really have it. So the important thing here is it does not matter what the ID of the water is. It does not matter because water can get exchanged, but what is of biological significance is if these three particular atoms, A, B, and C, do they have a significant, do they have a network for a significant amount of time? Again, the word significant can be used depending on the context. You can say water should always be there, and you can imagine that that's not going to be the case. Then you can say 90% of the time, 80% of the time, 20% of the time, something like that. So that significance is something that you decide based on a cutoff. But what we want to do now is we want to first find networks, and in doing so, we do not want to give any particular ID to a water across frames. So for example, this network in frame 1 could be through water number 1. In the next one, it could be water number 2. In the third frame, it could be water number 3, and so on. We don't care about it. What we see is that if there are 3 frames, in all 3 frames, there is some water. Water has no identity, except that within a frame, it is the same molecule, same water molecule that is actually bridging multiple atoms here. Okay. So, I mean, what do we, for example, you want to find if two people are working together or not. I mean, they could be working together. For example, they're transporting um, some packages together. It does not matter which package they are transferring, because in a day they might be transferring 100 packages, but they're always doing the same work. I mean, they're spending a significant amount of time together doing an activity where they're actually transferring packages. The package identity itself is not important, except that at a given point of time, these two are carrying the same package. Okay. So that is what we actually mean by network, and we'll use this concept to compute or rather to find if any water associations are there in a dynamical system. So the question is how difficult it is. It doesn't sound very difficult, probably. But then, even if you have big data tools that can work on very large number of systems and very large number of cores, this is such a problem that you cannot really write very simple code and get away with it. Okay. So whatever I'm showing you here was one of the two systems on which we have done benchmarking. So this one was the smaller of the two. There are 30,000 water molecules here that you see. There are 1 lakh atoms, and I mean, there are slightly more than 1 lakh. I'll give the exact numbers later. The number of frames is 1 million, and the total data size is 1.2 terabytes. And the number of networks that you'll come across, and rather we have come across, it's something that you cannot estimate. It is not known. We'll know only through analyzing the data. We have seen at least 5.5 million different networks. And then from them, we have to filter out the ones that are significant. Okay, so this is not a simple problem at all. For example, you have to consider all possible combinations of two atoms sharing a same water molecule. So you can see that even if you want to do that, you have to work something like 10, you have to do 10 power 10 calculations within a single frame. But then you can have 3 atom network, you can have 4 atom network. We have seen 5 atom and 6 atom networks also. So it's going to be very, very computationally, I mean, it will be computationally impossible to do a simple, straightforward kind of coding for that. So I'll tell you what exactly was a method that I have used to be able to solve the problem, and that too in a very limited amount of time. So just if you think you can solve this problem in 1 second, there is no way you can solve this problem within 1 second. But even if you do that, there are 1 million number of frames, and it would take at least 11.5 days to do the job. And we are only looking at frame-wise data. We are not even looking at after processing every frame, there is going to be additional work that we have to do in filtering. Even that, if you neglect, it's going to be a task that is going to be phenomenally, it's not a proper way of solving the problem. There are better ways of doing it. And there are much larger systems that are already there. If you go to Amber website, you will see that they discuss benchmarks on different systems. There are some systems that have 1,000, 10,000 or 20,000 atoms. There are some that have 100,000. And the one that I'm showing you here, it has 100,000 atoms. The second one that we have analyzed, again using big data approach, a similar one, had almost double the number of atoms. Here double means a terrible amount of increase in complexity. It's not just it's not going to be like if it takes 1 hour for 100,000, it's going to take double the amount of time. These problems increase something like n square or n cube, like square or cube, if you're not careful. Sometimes even if you are very careful, you may not have much luck given the nature of the problem, but we'll see how we have been able to solve this. So obviously the problem is so big that using normal straightforward coding is not going to be a very good approach. You can do it. You can play smart tricks I'm going to tell you, and you can cut down the time. But then even then, the time is going to be very, very huge. The reason why I would like to go for big data is we can, using big data environment, we can read multiple input files at a time instead of reading one at a time. We can write multiple output files. We can reduce the computational time by using multiple cores. For example, your mobile might have 8 cores, and the program that we normally write uses only one core at a time. So 7 cores are not being used at all. But big data allows us to use all 8 of them, and also more computers if you can provide. And also, it is scalable. Scalable in the sense, if somebody gives you, instead of 2 computers, if they give you 10 computers, you will begin to use all of them in a nice fashion. So probably your time of completion may not decrease 5 times, but there will be definitely an improvement. Okay. And we have used Spark, which can use Java-based libraries, and it is fault tolerant. I mean, big data is fault tolerant. So if one of the jobs get killed or one of the computers crash, you don't have to do anything. It will pick it up from where it left, and it will redo the computation. It is resilient to failure, and it will give you the output. So these are the reasons why industry has shifted to big data in a big way, and we are using that. We are using Spark for this, and there are multiple reasons for using it, but I'm going to skip them. The tools that I've primarily used are the following. One is Apache Spark, then there is SciSpark. It is something that can load the type of data that Amber generates, and it is not something that Apache can read. It is in a very specific, a very different kind of format called NetCDF. It is something that is used in big data environments like geospatial and so on. So NASA developed SciSpark, and then the language that was used was Scala. So there is an algorithm here, and what I'm going to do is, if you know big data and Spark, you can go through this, but I'm just going to translate what is being done here. So first we read the system details, the number of atoms, where they said what is the time and so on. We create frames in computer memory. We do it in memory because if it is in memory, it's very good. It takes much less time. For example, remember, the second line seems to be inconsequential, but that's not the case. If you go for alternate big data tool like MapReduce, they keep on writing the data to the hard disk. So what happens is, if you have to read 1 byte of data from hard disk or 1 byte of data from RAM, there is going to be something like 1,000 to million times difference in terms of performance. So keeping in memory is always going to be a very good idea in computer science. But then we are talking about big data, so we are talking about RAM of big systems and not something like mobile. We are not talking about GBs here. We are talking about terabytes. And the two facilities that we have here, one, we have a computer that, one, we have a server that has 2 terabyte RAM. The other one, we have 7 terabyte RAM. Remember that the data itself is 1.2 terabytes, right? So you have to be very careful in deciding what goes into RAM and what doesn't, and how you put it in RAM. And we filter networks. So we find networks in every frame, and then we put together to filter whatever that are significant. And then we decide, after finding, let's say there are 600 significant networks, we'll find for each of these 100, in which of these million frames we'll find them. So this is something that we have to do. Just give you a visual representation of what we are doing. So let's say each of them is a molecule, and if you see a network ABCD in, let's say, in 3rd frame, so that means there is one particular water molecule that has interaction with A, B, C, and D. Now the difficult part is, we use the concept of networks. A network is defined as two or more atoms, right? I mean, it can be two, it can be three, it can be four. I mean, we have seen even 7 and 8. So if you see ABCD, so all possible subsets with size or ordinal, so with at least two atoms, um, they also will be there. And finally, you may not select the biggest one that you see because they are too infrequent. You may select something that is slightly smaller but is there in larger number of frames. Okay, so if you see ABCD, that means you have to generate the subsets also. If you find ABC, you have to generate the subsets also, and then you put all of them together and then decide based on a cutoff which of them you are going to process. Now, there are going to be other interesting questions. For example, if you put cutoff as 40%, you won't pick up ABCD, but then you'll pick up ABC. Now, what do you do with AB and AC? Are you AB, AC, and BC? Are you going to retain them? Or are you not going to retain them? Well, it depends on the context that you look at. But these are the kind of questions that you have to address when you have the output, because your output is going to be also very big, and you should know how to even process that. So what is a trick that one can use to solve this problem in a very fast, at a very fast pace? So what you can do is you can solve the problem this way. You divide the space. I'm showing you in 2D. So there are a large number of molecules here. Each molecule is shown as X, and it's not X coordinates. It is shown as X. And we can divide, we can set the size so that there can be only one molecule at a time. So, but this is size of the grid. It does not mean there is going to be one. There can be more than one, because we have to take the maximum size, but never mind. So what happens is I go grid by grid and then I make a list of items that I have to look at to decide which of them will form a set. For example, here, whatever is shown as diamond, for this particular box or the grid, that is the square that you see, the only atoms that I have to worry about are X2, X7, X9, 51, and 65. They are sitting in the next one because there could be something here, there could be something sitting very close to that. So you have to look at the neighboring also. And if you're looking at 3D, you have 27 such boxes. So now every box can have only a finite number of water molecules, right? Because physically you cannot pack infinite number of water molecules in a finite volume. So that means this size has a maximum value. Doesn't matter what the maximum value is. It can be 1, it can be 10, it can be 25, or it can even be 100. But now what happens is you take one atom at a time or one water at a time, and you process only 100 of them to decide what are the patterns that you are going to see. So you can, I'll not get into how you can find, but then you can find, for example, this diamond has interactions with X2 and X51. And let's say the coordinate is not shown here. Let's say even X7. So you have ABC like situation here, then you can generate the smaller subsets and you have to keep track of them. And keeping track is a different challenge in itself, but then we can discuss it later if you're interested. The question is, those of you again who come from biology or chemistry or who have not forgotten their physics, hydrogen bond is defined based on distance as well as angle, right? Between three atoms. The center, the second one being hydrogen. So can we really neglect the angle part? Because that is not something we are looking at. We can, because what happens is if you are looking at those waters that are there for a long time, you can see the pattern here that distance is within the range of 2.4 to 3 for whether it is oxygen or nitrogen. And also the angle is about 120. So as long as you put these two conditions, that the distance has to be between 2.4 to 3 and 120 to 180 should be the angle, then you are safe. You don't have to worry about finding the angle. And that's saving significant amount of computation as well. So doing this, what were the results that we obtained? Right? What were the surprising things? I'll tell you one very surprising thing at the end. The system size of the two that I mentioned. One of them has had 1,93,000 atoms, the other one 1,85,000. The number of frames is something like 1 million, that is 10 lakhs in the first one and 2 lakhs in the other one. And what you see are various types of molecules. And, big data analysis was really required for this problem, not just for water, as I'm going to show you, because in the way and the properties of interaction between a molecule with its ligand is such that it gets affected by its environment. This has been known for a long time, not just the interaction, but also almost all biological and biophysical properties can be affected, including folding or reactivity, or you name it, you name a parameter that can get affected by what is called as macromolecular crowding. Cytoplasm is not what your textbook in biology would have shown you if you have done schooling only in biology. It is very crowded. Only 40% of the space will be left for movement. So it's very crowded. It's like Kumbh Mela that is going on. And we should be grateful that any work gets done in such a crowd at all. But besides the point, we have to understand, decipher what are the interactions that are going on, and conventional tools that are there. They are not great for this kind of scenario where there are, 100 or 200 different types of molecules, because we do not know which one will bump into which one and how long they are interacting and so on and so forth. All interaction need not be hydrogen bond, but you can use whatever that we have discussed here, the same idea, to solve other problems also. You can see that this speed has phenomenally improved. So against something like 8,600 seconds, we could do it in 273 seconds. For water networks, the difference is almost 1,000-fold. Okay, so that is a kind of performance benefit we were able to derive. And if you see some of the reviews on drug design, they always talk about two things. We have to understand how drug behaves within a cell, which is very difficult to study, and also whether there is going to be a water that's playing some spoil sport. So we are able to identify from our simulation such kind of motifs also. GLC that you see here is a drug. So these are two different molecules from protein, and here you see there is a water molecule. So one that people have been saying for a long time is important. We've been able to do that, and also we're able to, find the molecules that are interacting in very specific sites, and we know we are able to derive. We've been able to derive when some particular molecule is interacting with which particular molecule on protein or RNA or DNA whatsoever. We know what to look for, because it's a very crowded environment. Unlike normal simulation where you can play the movie and see, it is like Kumbh Mela, and you cannot really understand who is with whom. It's not at all easy. You don't know where to look and whom to look for. The most surprising thing that we have seen, and something that we are very glad about, is when you see how much movement is there for every residue, and then there are about 600 plus residues. Almost all the simulations, each line here is a different simulation. Some of them are in water, as you should see in aqueous. Some of them are in physiological conditions. Some are in conditions where only small molecules are added, not the big ones. So all of them seem to have the same kind of pattern, except in some cases there is a very big deviation. And we've been able to associate those outstanding or very unique deviations in some particular simulation with interaction of one or more molecule that interacts with it. And sometimes even that interaction might be very, might be for a very small time, but then it's just like, they come, they interact, and they change the dynamics of that particular segment of the protein. These are all the beads on the polymer that are they got deviated. In fact, there are two of them, and in both cases we've been able to associate two different molecules that have actually interacted. So we have been able to get this kind of insight only because of the approach that I've shown you. This is the final slide, and here the most interesting thing for me, and it's very glad I'm glad about it, is we have just sent it for we have submitted for publication. So if you look at the active site for this particular protein, which is called as main protease of SARS-CoV-2. So this particular water is described as the third residue, catalytic residue, by the authors of Nature paper who solved this structure. So we've been able to see it being conserved under all different types of environment, and also it's conserved in 8 very high resolution crystal structures. So that is something that we have seen. And also when we looked at isolated waters, that is waters that are interacting with this protein, but not with any other water. When we looked at them, there are only 4 such waters we have found out of hundreds of them. Out of 4, 1 of them is the catalytic water. And compared to the other 3, catalytic water was 50% more likely to be secluded from other waters. So it is something that is very, very interesting. Out of hundreds of water molecules that we have seen, there are only 4 that are special. They are always there. It doesn't matter what the environment is. Of course, the catalytic water won't be there if you put a drug there, but if not, you'll definitely find it. And what we have seen is the other 3, if they are there only 60% of the time secluded from other waters, catalytic water was like 90% secluded. So if it is there only interacting with the protein and not with any other water. So that is something that is very special that we found and we are excited about. And we are able to do that only because of the technique that I just explained. So this is what I wanted to share in this workshop regarding the modeling of problems for big data. So spatio-temporal, we say because we look at problems that have defined both in terms of space, like XYZ coordinates, and also over time. The system evolves over time. So that is what I wanted to discuss in this workshop.